Hi everyone, this is an example of a redox stoichiometry problem. Here we go. In a titration experiment, 15 milliliters of 0.300 moles per liter acidified potassium dichromate was used to oxidize basic sulfite ions into sulfate ions. If the sulfite ion concentration was 0.400 moles per liter, what volume was used? This is quite a question. Our first step is to determine the net ionic equation. We're going to follow the 5-step method to do that, which begins by making a list of all of the substances that are present. It's acidified potassium dichromate. Acidified, put hydrogen in your list. Potassium dichromate's an ionic solution, it dissociates. We're going to have to put water in our list too in a minute. We're going to have basic sulfite ions. Basic, that means put hydroxide ions in your list, and we have sulfite ions. Because we also have all these aqueous solutions, put liquid water in the list too. Make a list. Label all of the oxidizing and reducing agents. Hydrogen alone is an oxidizing agent. Potassium alone is an oxidizing agent. The hydrogens and the dichromate together are an oxidizing agent. Hydroxide alone is a reducing agent. Hydroxide ions in combination with the sulfite ions are a reducing agent. Water is both. Okay? After that, out of all of the oxidizing agents, which one is the strongest? Here. Again, as a pro tip, as soon as I see acidic dichromate in the question, I could skip all of this and go straight to that half reaction. I don't have to label all of these oxidizing agents. It is going to be so common for acidic dichromate to be our strongest oxidizing agent. Also be on the lookout for permanganate. Copy down the oxidizing agents half reaction right out of the data booklet. We've seen the acidic dichromate so many times, you're going to start to remember it. That will help speed things up. We're copying down the strongest oxidizing agents half reaction right out of the data booklet. Out of the reducing agents, which one is the strongest? That's the one that's lowest down on the right-hand side of the data booklet. It's here. The combination of hydroxide and sulfide ions. That's also implied. The reducing agent gets oxidized. And what happens? We're going to oxidize basic sulfite ions. So the wording there of the question gives us a bit of a heads up that we must have made a correct decision here. We need to copy down this half reaction in reverse from how it shows up in the data booklet. It's SO3 minus aqueous and 2 hydroxide ions. Two electrons. It's very important that the two half reactions we've written down here, one of them has to be reduction, one of them has to be oxidation. Our next step is to balance the electrons, 6 and 2. Multiply that by 1, multiply this one by 3. Okay. By balance these electrons, I'm going to have 6 electrons on the left-hand side and 6 electrons on the right-hand side. They're going to cancel off. Looking ahead, I see that these two half reactions have a second chemical in common. It's this water. But the water in the first half reaction is on the product side. These water molecules down here are also on the product side. They're going to group together as we add the half reactions. Let's look at what's going on with the water. Here's 7 liquid waters multiplied by 1. That's 7. Here's 1 liquid water times 3. That's going to be 3 waters. 7 waters in the first half reaction, 3 more in the second half reaction. That makes 10. Pretty intense to come up with these 2 half reactions leading to the net ionic equation. Both the oxidizing and reducing agents were these combination ones. That's a little bit tricky. We might have overlooked that. We had grouping, we had canceling. We have a pretty long net ionic equation. It's implied that it's spontaneous. The question is saying the reaction did happen. The oxidizing agent is also higher than the reducing agent in the table. Now we can move on to the math. Find the moles. Concentration and volume, and concentration, we can multiply those together. Make sure that we have the volume in liters. It's going to give us the concentration multiplied by the volume in liters. We're going to multiply by the R over G. What we're trying to find in the end is the volume of the sulfide ions. What's required was this second half reaction, which was balanced with a 3 and the 1 for the dichromate. So here we have a 3/1 ratio. In our last step, we're looking for the volume, so we're going to divide by the concentration, which was 0.400 moles per liter. We can calculate away, we can take our time, there's lots of buttons to push. 0.03 times 0.015 times 3/1 divided by 0.4. .003375. We need to apply our significant digits. The 3 numbers in the question all have 3 significant digits, so we want to round off our answer here so that it also has 3 significant digits. We can keep it as a decimal. We are not required to change it into scientific notation. We could if we wanted to. And we have the units here. We found the volume. This is liters. When we're going through the process of answering a redox stoichiometry question, it's really, most of our work happens just determining the net ionic equation. The math itself isn't so burdensome. Really make sure though that we do make sure our volumes are in liters. Watch those significant digits and units. And I hope that helps.